All right, everybody, by my clock, it is 7 o'clock Mountain Time, and that means it is time for us to get started. So I am going to go ahead and kick us off, starting off today by saying hello and welcome, and thank you so much for joining us tonight for Looking for Life on Mars, a special presentation all about the Mars 2020 mission and the people and the organizations that make it possible. We've got three amazing scientists here to talk with you this evening. I'm going to have them start their cameras up to give you a little wave just so you can see their face. You'll get to hear from all of them in turn, and they're going to present about their unique role in this mission, what they bring to the team, what they're hoping to learn. So tonight we have Dr. Steve Lee from the Denver Museum of Nature and Science. After him, we'll hear from David Buecher from Lockheed Martin. And then after that, we'll hear from Mike Wolff from the Space Science Institute. So all three of these gentlemen are going to tell you about what they know, what they're excited to learn about, why are we sending this thing to Mars, and hopefully we'll get a chance to answer as many of your questions as possible. We're hoping that we might be able to run a little bit long tonight. We know that a lot of folks often have a ton of questions about events like this one. So we are looking forward to getting to as many of those as possible, even if it pushes us a little past 8 p.m. So settle in, get comfy, because we're diving deep into the science tonight, folks. My name is Talia. I'm the Virtual Experiences Coordinator at the Denver Museum of Nature and Science. So my role in this program this evening and throughout other events that perhaps you've gotten to see before is to bring your questions, bring your comments to our experts. So that's what you're going to get to see me doing tonight. I will be introducing all of our specialists as they give their presentation. Mike is already watching the chat. I can see those questions are already starting to roll in. So yeah, we're going to have a lot to answer tonight. My role will be to introduce our experts, keep us moving through a packed schedule. We've got a lot of science to cover tonight. And then of course, to bring your questions to the experts. If you haven't already done so, take a moment to type in that chat and say hi. That's how you're going to be communicating with us all throughout the evening tonight. So figure out where it is, get comfortable using it, because that's where we're going to be going to pull your questions, your comments, the things that you're excited to hear a little bit more about, and your reactions too. We want to hear from you. So send us as many comments as you would like, throughout the event tonight, and tell us where you're watching from tonight. It's always great to know who is watching from maybe their back porch or their couch with their dog or cat. And it's always great to hear too about people watching from other states. So send us a chat, say hi. We always love to get to hear from you. Without any further ado, I am going to kick it over to our first speaker of the evening, Dr. Steve Lee from the Denver Museum of Nature and Science. Steve is a planetary scientist and Mars expert. Steve, how long have you been with the museum? I always forget the number.
Gosh, it's coming up on 19 years now.
There you go, 19 years. So he has been a blessing to the museum for just about that long and will continue to be for long into the future. So Steve is going to kick us off tonight by telling us a little bit about the mission, giving us a little bit of context, telling us why are we going to Mars? What's so interesting about this red planet? You know, it's just a hunk of iron, right? Hunk of iron and dust. No, it's a lot more than that. And he's going to tell us exactly why. So I'm going to hand it over to Steve. After that, we will hear from David. And then we also do have Tatiana Burden from Lockheed Martin in with us tonight. She's going to be helping with Dave's presentation. So you may get to hear her once or twice. We'll hear from them afterward. And then after that, we will talk with Mike Wolff from the Space Science Institute. Again, jam-packed schedule, and then we'll be ready to take your questions. All right, Steve, how are you doing tonight?
Great, and you just gave most of my talk, so this will be a lot shorter than it would have been. What I wanted to do is just give an overview of why we're sending the Perseverance rover to Mars. A little bit about what we know about Mars and comparing Mars to the Earth. So I think at this point, I'll switch over to my slides, which will take hopefully not too long. There we go. So this is just an artist's drawing of what the Perseverance rover will look like when it's sitting on Mars. And for those of you that are Mars buffs, you'll notice this looks a whole lot like the Curiosity rover. It's not quite an identical twin. It's got very different instruments, so maybe I'd call it a fraternal twin. The basic spacecraft and structure is the same, or very close, but the instruments on board are very well tuned to this particular mission. So I want to go into that. So just to set the scene, today, Mars, even though it's the most Earth-like planet in our solar system, it's essentially a very frozen, cold, dry desert. And what's puzzling about that is we know, looking at the planet from orbit, that there must have been a lot of water there at some point in the past. We see dry riverbeds, we see dry lake beds. There's ice in the polar caps, but there's very little water elsewhere on the planet, and no liquid water on the surface at all. It's just the atmosphere is too thin and too cold to support that. So here's what we think Mars might have looked like perhaps 3.5 or more billion years ago. It seems like all of the a lot of the observations are pointing to a planet that maybe had oceans, certainly had lakes, certainly had rivers, and somewhere in the last 3.5 or so billion years ago, it turned into the Mars that we see today. We have several missions that are looking at the details of how that change happened, but this particular mission really is designed to look at astrobiology, look at the possibility that when Mars was warm and wet early in its history, that possibly simple life could have arisen on the red planet. And so just another comparison, if we look at the age of rocks that we've recovered on the Earth and compare those to Mars, we see that the surface of Mars is considerably older than on Earth. Looking at all of the continents, these gray areas, and in particular the ones highlighted with the yellow dots, those are the oldest rocks that we have on the Earth. But most of the Earth's surface has been resurfaced by plate tectonics over the years. So the bulk of the crust that we see in the continents is much, much younger. But from these ancient rocks on Earth, I'm sorry, I went ahead too fast. Notice on the upper right here, there's a note that at least 50% of the surface of Mars we think is older than 3.6 billion years in age. And looking at the Earth, that is a very rare occurrence to get anything that old. So on the Earth, if we do a sort of a fairly simple timeline of when the Earth first formed and when biology popped up, we see that roughly at the 4 billion year ago point is when the first simple organisms, single-celled organisms, arose on the Earth. And then it took 3.5 billion years, roughly, before we got two-celled organisms. And so life had to cook for a long time in the Earth's oceans and swamps before it got more complicated. And so when we're thinking about another planet, what should we be looking for? We know on the Earth, we've got what I guess I'd call a classic fossil, leaves, fish, dinosaurs. All of those end up, when we date them, being less than about 600 million years. But if we look for the signatures of single-celled organisms, what we call microbial biosignatures, the oldest of those signatures ends up being about 3.6 billion years on the Earth. And the form of the most ancient of these signs of primitive life on Earth are what we call stromatolites. This is an example of modern stromatolites being formed today. It's in a bay on the coast of Australia. And what these lumpy rocks are is where you've got, for lack of a better word, it's almost pond scum. You've got mats of bacteria, mats of algae, mats of single-celled organisms, and there's a little bit of sediment, mud, for lack of a better word, that gets incorporated in these mats, and then the mat grows another layer on top of that, and it sort of forms these big knobs. But when you look inside those, here's an area in Western Australia where they found fossilized stromatolites that are 3.5 billion years old. And when we cut those open and look, you see this very finely layered structure to the rocks. And when they actually look at the composition of those layers, we can come up with organic molecules, biomolecules that say that there was life involved in making these stromatolites. And so if we try to expand this to elsewhere in the solar system, like Mars, we might look for things like stromatolites if it was wet enough that you had enough water for these to grow in. And so there's the physical shape of these things. There's the structure of these rocks. There's also the chemical signature. But in addition to that, we have some minerals that are just caused by life, like these little nodules in the center image. Those involve bacteria rising things like iron and reprecipitating it into these very regular, very tiny little spheres of iron minerals. And we also can look at the composition of the gases that are given off when we cook some of these samples. And we just look for the chemistry of life. And a prime place to find that on the Earth is any place that we have rivers emptying either into lakes or oceans where we get a delta. So we have water flowing. Water is one of the required ingredients for life, at least on Earth. And then we have these very fine sediments that if there are bacteria or simple organisms, they can get buried in this sediment and preserved over time. And so what I wanted to do is now move to Mars, and we'll start talking about the mission that's launching on Thursday, the Mars 2020 mission. And so this is a very nice couple-minute overview of how this mission is going to be searching for biology on the red planet.
You know, Mars is the closest place that we can reach with robotic exploration that we think had a really good chance of having ancient life.
The Perseverance rover will land at a location called Jezero Crater. Jezero Crater is a very interesting place. It's a crater that once held a lake.
There are a lot of craters on the surface of Mars that could have once hosted ancient lakes, but not every crater that we think had a lake actually preserves evidence that that lake was there.
It had an inflow channel and it had an outflow channel. That means it was filled. The crater was filled with water.
In Jezero, we have probably one of the most beautifully preserved delta deposits on Mars in that crater.
This is a wonderful place to live for microorganisms, and it is also a wonderful place for those microorganisms to be preserved so that we can find them now so many billions of years later.
There is no other place on Mars that has the unique combination of a lake setting, a beautifully preserved delta, and the diverse mineralogy that we have in Jezero Crater. So it's truly a special landing site.
The major goal of the Perseverance mission is to investigate astrobiology on Mars, and in particular, to address the question of whether life ever existed on Mars. The Perseverance rover starts with a design that's very similar to Curiosity, but we've added to it a whole new set of science instruments. And these science instruments were purposefully selected to help us in the search for biosignatures.
We're going to be taking microphones with us. For the first time, we're going to have that human sense on another planet.
Perseverance carries with her a grand experiment in spacefaring technology, a helicopter, the name of which is now Ingenuity.
One of the major upgrades that Perseverance has from Curiosity is that it's able to self-drive for a distance of up to 200 meters per day. As the rover is driving, it's literally building the map of the road it's driving on Mars.
Scientists for years have told us that to really unlock the secrets of Mars, we have to bring samples from Mars back to Earth.
So what Mars 2020 is going to do is to drill samples, put them in small tubes. We're going to seal it in its own individual tube. We set them on the surface to provide a target for the second two missions, which hopefully will get in development in the next several years and could potentially get the samples back to Earth by 2031.
Perseverance is a very, very profound first step in both our understanding of our place in the universe and a stepping stone towards human exploration.
All right. So that gives you the quick overview of what we're hoping to accomplish with this mission. It's actually got lots of different goals, and I think Mike will be telling us a bit more about the science that we expect to be going on. And Dave will be talking a lot about the engineering of this mission. So I just wanted to end with just a quick look at what's been happening in the course of building this spacecraft, and then finally getting ready to launch it on its way to the red planet. And so just to give you a feel for the scale here, this is a family portrait of the rovers that we've sent to Mars. In the lower left is the little Sojourner rover. It was part of the Pathfinder mission and landed in 1997. That's about the size of a microwave oven that you might have in your kitchen. Above that is the Mars Exploration rover, Spirit and Opportunity. Those were about the size of a golf cart. They both landed in 2004 and survived until just a couple of years ago. So a lot of great science from that. Those rovers determined that there had been liquid water existing on the surface of Mars in the landing sites for them. So that was a major accomplishment. And then on the right here is actually the Curiosity rover, the same size as Perseverance. It's about the size of a Mini Cooper automobile. And what Curiosity has found in its mission, it landed in 2013, it found that the environment where it landed was habitable. It was the type of environment that could have supported life. And so then this next big step will be actually looking for signs of life itself. So here's another artist's view of Perseverance on the surface. It's got a very long robot arm that can reach out and sample the surface and measure the chemistry and the minerals and the microscopes, things like that, and collect these samples that we talked about. And so here's the actual Perseverance getting ready to be shipped to Florida. It was built in California at NASA's Jet Propulsion Laboratory. Here it is in Florida, getting ready to be all buttoned up. And I think David will talk a lot more about this. A lot of the structure you're seeing here was built here in Denver by Lockheed Martin. And so here's the spacecraft all ready to seal up into its payload fairing. So these are the sort of clam shells that protect it as it flies through the atmosphere on launch day. And here it is all ready to go. It's being just like, a delivery truck. These large vehicles just roll the spacecraft and its fairing out to the launch pad that you see off in the distance there, and it gets stacked on top of the launch vehicle. And so this is a picture that was taken earlier this morning. So there's Perseverance sitting on top of its Atlas V, almost at the launch pad. And so tonight it's at the pad and ready to go on early Thursday morning. And so here's the time. If you folks are really excited about this, it'll launch just 10 minutes before 6 a.m. Mountain Time. We will be doing an event here at the museum, another virtual event, just again describing the mission and then having live coverage from NASA TV. And so join us on Thursday for the first major step of this mission to get it sent on its way to Mars. And we'll show this at the end of tonight's program as well. But if you are interested in a lot more information, any one of these three websites can give you updates, give you lots of materials with details about the mission and progress from the mission. So I think at this point, I'm going to turn it back to Talia and have her introduce David.
Fabulous. Thank you so much, Steve. I think your expertise about Mars is really important in defining the big questions here, right? Like, what are we doing here? Why are we sending this craft out to the red planet? Why are we sending this to Mars? What are we hoping to learn? So thanks for giving that crucial context to the audience. I'm going to go ahead and stop your screen share, and then I'm going to have David start his camera and give a big wave to the audience. Welcome back. We are so grateful that you're here tonight. And Tatiana, we might hear her voice at some point. Otherwise, she is driving things behind the scenes. She's got Dave's slides up. So I'm going to do a quick introduction before we get started. Dave Buecher has worked for Lockheed Martin for 19 years, holy wow, in various capacities, everything from management to mechanical engineering and to systems engineering, and at various campuses, so everywhere from Sunnyvale, Star Labs in Palo Alto, and Denver. And over that time, he has primarily worked on many of the NASA planetary exploration programs, so he knows a thing or two. He has supported the Mars Science Laboratory Program, Juno, MAVEN, InSight, Mars 2020, Mars 2020, MHDS. You might have to tell us a little bit more about what that one means, Dave. And now Europa, Clipper, and Dragonfly. So what a fabulous resume. Each of these projects has brought its own technical challenges and opportunities. And during his time at Lockheed Martin, Dave has had the great privilege to work with many talented engineers, leaders, and coworkers that have shaped his career and growth. So it is my pleasure to introduce Dave Buecher from Lockheed Martin. He's going to tell you a little bit about Lockheed's role in the Mars 2020 mission and what we can expect on Thursday.
No, I'm excited to be here. Thanks for having me. So my overall role on Mars 2020 was to design the hardware that separates, I'll cover it in a minute here, that separates the heat shield from the back shell, the aeroshell, as well as the program manager for the MHDS program, or the Mars Helicopter Delivery System effort. And we'll cover that here in a little bit. So why don't we go ahead and jump to the next slide. We've got quite a few slides and I'd like to get through them and explain it. So who's Lockheed Martin and kind of what is our role? So Lockheed is a big global company, corporation. We have approximately 110,000 employees across the world in 4 major lines of business. We have aeronautics, we have missiles and fire control, rotary and mission systems, and then my home, which is in space. Within space, we do all sorts of different supportive roles. We design, build, test, and fly the spacecraft, as well as doing different elements, like on this program, where we'll design and build and test and deliver elements of a program as well. And we're looking forward, this is kind of a stepping stone, as alluded to in that video, of what's coming next. Mars is a big interest to the world, and we really want to understand it, but we also eventually, our goal is to send people to Mars. And so Perseverance is just another step in that path to ultimately sending people to Mars. Next slide, please. So what has Lockheed Martin's role been in explicitly with Mars? So we have been on every planetary mission so far in some capacity. Specifically for the landers, we've done 5 different landers to Mars. We've had 6 different orbiters. Some of those are still in action at Mars, such as MAVEN and MRO, or Mars Reconnaissance Orbiter, still performing, still having extensions to their lives, doing what they're out there to do as either science or as communication relay stations for the landed missions. We also have a number of aeroshells, and that's what we're going to talk about here, because that was our main role on Mars 2020. And aeroshells are basically a protective system that allows you to get a payload down to the surface of the planet. So for Mars, we build an aeroshell, which has a heat shield half, which is the bottom half, and a back shell half, which is the top half. And in this case, the rover lives inside of that. And this aeroshell safely gets it through the atmosphere, protects it from the heating and ablative environment of passing through that atmosphere. And then it gets released, it gets separated to allow the rover then to go ahead and, in this case, fly itself down to the surface with the descent module. And so Lockheed Martin's role in this program, well, we'll get to that in a minute here, but in a lot of these programs have been varied, whether we're doing the aeroshell, orbiter, and lander, or the crew stage and so forth. And we're, over our experience and time, we've been very happy to partner with NASA and different missions to be able to investigate and learn more about our solar system. Next slide. So what do we do directly on Mars 2020? As I said, we did the aeroshell, focus on that center picture. So the bottom half on that center picture shows the heat shield, and the top half shows the back shell. the white part. The bottom half, that heat shield that you see in the left-hand picture there, has some thermal protective system called PICA, or it's a phenolic impregnated carbon ablator system. And what that does, basically, as it goes through the atmosphere, it ablates, or it slowly sloughs off that layer due to the heat and pressure, and it allows that energy to be released instead of it coming all the way through and heating up and say burning up your system coming through on entry. And so the heat shield is a very critical element in that entry process. And on the back shell, you also have a thermal protective system. In this case, it's a super light ablative material called SLA, and it allows for that back stream of the airflow and heating. It protects the rover from that backflow and the eddies in that side. And then as it goes through, as I said, the rover will command the sequencing of the releases. So the aeroshell will safely get it through the atmosphere. Then the parachute will go ahead and deploy. The rover commands the parachute to deploy at the top of the aeroshell. The heat shield will then be released by the rover, and there's 9 separation fittings that hold the heat shield to the back shell. Heat shield gets kicked off, and then it continues to decelerate, and then the rover releases the descent stage from the inside of the back shell, and as it flies itself down to the surface, and say that descent stage releases the rover and it flies off. At the bottom of the rover for this mission, we have, for the first time ever, a body that's going to, or craft that's going to fly on another planet. And that spacecraft, or that item, is a helicopter in this case. And it's named Ingenuity, as you heard in that video. It'll be the first time we've sent a helicopter to another planet to fly. It's not necessarily your traditional style helicopter. As you see in that picture, it has counter-rotating blades on the top half, and it has a box structure as its base. It doesn't look like a standard helicopter or a quadcopter. At any rate, at Mars, with the light atmosphere that it has and the 3/8 of a G, or 3/8 of gravity environment that you're flying in, that helicopter had to be weight optimized and lightweighted as best as possible. And that's why you see it's a very refined and lightweight structure. So our role with that was we had to get that lightweight helicopter down to the surface and then protect it until the rover was ready to deploy that helicopter. So we worked and partnered with JPL out of Pasadena, who's doing the primary mission on the rover, to understand the helicopter, understand the interface of the helicopter, help refine those interfaces, and then ultimately help design a system that would retain that helicopter, that would have a composite cover called a debris shield that would help protect that helicopter as that rover is coming down to the surface and driving around. But then ultimately, when the rover is ready to release it and has found a good place for it to fly from, it'll then release the debris shield, that cover. It'll drive to the spot that it wants to release the helicopter. Then that Mars Helicopter Deployment System, or MHDS, will then be commanded to go ahead and release the helicopter. Helicopter will be released, and then it can fly around independently of the rover. And so our role was mainly those elements: the aeroshell system, the separation hardware for that aeroshell, as well as the protective and delivery system for the helicopter. Next slide. So at this point, we're going to show a video of the helicopter, and as well as how it deploys.
And folks, that may just take us a moment.
So as you can see, it's pretty exciting stuff that we got to do. We got to work with, say, outstanding organizations between JPL and Lockheed Martin as we work through that helicopter, first the development of it and how we're going to incorporate it, but also the whole development and design and iterations of how to incorporate that onto the bottom of the rover. And I know, say, myself and my program team, we felt very honored to be a part of that. And every time I see that video, really anything to do with the helicopter or the rover, I'm pretty excited. I'm pretty excited for this Thursday for it to launch, and we're pretty excited for it to go forward. So next slide, please. So what's next? I get asked that a lot. Well, what's next is, say, Mars, Perseverance, and Ingenuity are both stepping stones of the overall plan for Mars. And Perseverance is going to go ahead and cache samples such that we can send those samples hopefully back to Earth here by 2030 is the goal so far. So what's next is the next set of missions. The next set of missions is going to be called Mars Sample Return, and they're working that out now. They're working out how they want to achieve that, what infrastructure they need up in space to achieve that, and how and what elements can different companies bring to the table to help make that goal a reality. And so I know just at a high level from what I've seen publicly from NASA, I'm looking forward to hopefully this coming year or this coming year for more announcements on what their next plans are of moving on to getting those samples back from Mars and understanding a lot more about its chemistry and its geology. And next slide. And with that, thank you very much for having me on, and I'll turn it back over to you, Talia.
Thank you so much, Dave. That was wonderful. It's really, I think one of the things that's most incredible to me about this mission is how dynamic and how many different things it's going to be studying. You know, I know a lot about Cassini and Huygens, and that's what this is reminding me of, you know, two components that are going to hopefully really deepen our understanding of a place we know a little bit about, but that we still have a lot to learn about too. So next up, we are going to hear from Mike Wolff from the Space Science Institute, and I will have a bio for him shortly. So I'll have Mike go ahead and bring up his smiling face on the camera. He has been busy already this evening answering everyone's questions in the chat. So if you have sent us a question already, he might have typed you a response. If he hasn't gotten to it yet, perhaps we'll get a chance to answer it a little bit later, but I know he's already been busy, so thanks, Mike. As a quick introduction for him, Mike Wolff is a co-investigator on the Mastcam-Z investigation. He's a senior research specialist at the Space Science Institute, where his research interests focus on aerosol properties in the Martian atmosphere and the development of analysis techniques for spacecraft observations of planetary atmospheres. So he's an atmospheric scientist. He's been involved in several past and current Mars missions, including the Mars Exploration Rovers, the Mars Reconnaissance Orbiter, the ExoMars Trace Gas Orbiter, and the Emirates Mars mission. And of course, a very important fact for everyone, his favorite color is blue. Kids, believe it or not, will ask that question of scientists a lot, so I love that you included it. How you doing tonight, Mike?
I'm doing well. I hope everyone else is doing well. We've heard lots of great stuff and all sorts of cool things about the hardware. And what I'm going to talk a little bit, very briefly, are the tools and the process. And I'm hoping this produces more questions later, because at the end of the day, or the beginning of the day, you have a bunch of scientists who sit around and try to figure out how best to use a tool like the rover and its tools on board, and how to accomplish its goals. And Steve has talked a little bit about these, and we'll see them again too. So you saw this picture already. The whole idea of a rover, you should think of it as a robotic geologist. I'm an atmospheric scientist, but some of my best friends are geologists. But we're going to talk mainly about rocks. I'll try to put in a plug for atmospheric science as we move along, but many of these very exciting developments are focused on the geology. And so when you think about what does a human geologist do, a human geologist has to move around. Wheels, you have to be able to see, you have to have tools. If you're a geologist, you have a rock hammer, a magnifying glass, you know, old school. Maybe you bring samples back to the lab to do more. So in this sense, Perseverance is very much a geologist with occasionally an atmospheric hat on. So we're going to look at some of these instruments very briefly, but to give you an idea of what they do and how they'll help. Steve showed an image very similar to this, and just for scale, The one on the right is the Curiosity, or a model of the Curiosity rover, which is essentially the same as Perseverance on the outside. It's just the inside, the tools that are different this time around. And you can see how much bigger things have gotten. And as things get bigger, they become more complicated. So I was initially involved with the rover on the left, the Mars Exploration Rover, and there were two of those. They landed in 2004. And that operational process was much simpler. You know, we sat around, you'd figure out what you want to do. You'd find out this geologist wants to do this and this group wants to do that. And you would start to horse trade. And if you do atmospheric science, you quickly learn you get the best data at times the geologists don't want to use. And so you would make deals. I won't ask for this, you'll do that. But moving to the much bigger rover, it's become more formalized, or the processes are more complicated, but also more technical and more precise. And we'll talk a little bit about that, maybe there'll be questions, but there's always a human in the loop. Now, the rovers are designed to stop themselves from crashing into things when they're driving in their auto nav or self-driving mode. So humans aren't actually controlling a joystick, which is always a fun thing in cartoons, but in fact, they send commands. If anybody in the audience has children, or they're, remember from doing Lego Mindstorms robotics, you had to program this rover to do various tasks. And it's very similar. You send a program to the rover and it does it, unless you make a mistake. And then sometimes it can help that. But there's generally always a human in the loop. So one of the big things that you have to do is you have to be able to see. There's a very high resolution camera, and what's new this time around is the focal length changes. It can be telephoto or it can be wide angle, and even people using iPhone cameras. You look onto something, you want to zoom in, you spread your fingers apart, and suddenly you can see the object up close and you can take a picture. That is essentially the same thing that the Mastcam-Z will be doing. It'll be able to take pictures and see great detail, even as far away as 100 meters. And that might inform whether you want to drive in that direction, there's a cool rock, or maybe there's a problem and you need to go around. So being able to see where you want to go is an important aspect. Plus it can see in many different colors. So it can provide information about rocks that are in the distance that may flag them as potentially interesting. The SuperCam. Well, other than an exciting name, this is interesting because it looks at many different wavelengths of light, but it also has a laser. So it combines just looking at things like a camera, and it actually has a little camera inside it as well. But with the laser, it can actually sample things that are out of reach. In other words, its laser can vaporize a rock, and then the camera system looks at this vapor, this plasma cloud, to see what's in it. So it can study rocks that are far above where the rover would be able to reach otherwise. So it's a way to learn about the composition of rocks, both at the atomic and the molecular level, to understand composition. If you're a geologist, it's all about the rocks, but there are many aspects of what the rock looks like, what it's made out of, where is that rock in relation to other rocks that you've studied. This is just one way to look at them in greater detail. There's something called PIXL, which essentially uses X-rays to figure out which elements are in a rock. So you can you see there in the picture, it's getting up close to a rock and at very high resolution. So things that are very small can be probed by the X-ray, gets hit with an X-ray, and the material gets excited and emits X-rays itself in a certain way to identify which elements make up that rock or that sample it's looking at. So a little bit like SuperCam, but using different wavelengths. Something called SHERLOC, which is yet another, we'd say, spectrometer. It has a laser itself. It looks in the UV. One of the things it's really designed to do is to look for organic material, right? You can have organic material, which is very exciting. Doesn't mean something was alive or degraded into this material, but it means there are the materials there to perhaps have contributed to environment conducive to life. You always have to use words like that when you talk about this. And since I'm not an expert, I am not going to go out on a limb here. But it's another way that as a robotic geologist, Perseverance can wander around and try to put together a story of the area it's exploring. And we'll see what that means, because it's going to explore many areas with the goal of finding kind of the coolest samples that are worth to bring back to Earth. Watson, I got a question about whether if you had a microscope on the rover, it would be able to see a microorganism. Well, this is like any microscope. If something is there, it will see it. And this is on the arm at the end. And this is a fairly advanced one. It has color, so it can see red, green, and blue. It sees very high resolution, and it can move around, so it can create stereo, which means it can produce 3D structures, or give the scientists information to see what the structure of a rock is, or parts of a rock. And any information about the rock, what's in it, what's its structure, gives clues to its history and what might have happened long ago on Mars when the climate was much more conducive to conditions that we think are favorable to life. And instruments can work together. So here basically what you want to see here, these are different types of data from all three instruments, and you can see some of the same structures. In other words, they're telling you something different about this rock, and it's these curvilinear structures. And each instrument gives you a different piece that helps you unravel what happened. On the Earth, when you have layers, it's often associated with a sedimentary rock, and that's very exciting. Often there was water involved, something was eroded and it was deposited. So it becomes very exciting from the geological perspective. It has a radar, ground penetrating radar, which means this one can go down to about, I'm going to get my units wrong here. I think it's 30 meters. And so what it does is it sends radar waves down into the surface, and by looking at changes in the reflection, and you can see here this white part is giving a little schematic of what the data looks like. It sees dark areas and white areas. What you see are places where the radar is absorbed and where it is just transmitted easily. In rocks and ice and even liquid water, they all have different properties. So it is a way to make a connection with what's happening underneath the surface to what is seen at the top of the surface. Or the top of the surface, at the surface. And here's a very exciting instrument. I mean, in addition to the Mastcam-Z that we saw before, it has a camera, it can look up, it can look sideways, it can look at the sky. This is an instrument called MEDA that is designed to actually study the atmosphere exclusively. It is essentially like a mini weather station. It has atmospheric pressure, wind speed and direction, relative humidity, ground temperature, air temperature. It can do, as well as it's got its own set of cameras to monitor the sky. So this is an instrument which I personally will be working with the data from in great detail along with Mastcam-Z. But this is essentially a weather station on Mars. Understanding the weather on Mars now is important to be able to make predictions, whether we're talking about people going there or 3.5 billion years ago, when we think things were very conducive to life. If we can't understand the weather now, it's a lot harder to go back and understand what it might have been like 3.5 billion years ago. There are all these pieces of the puzzle are linked together. And this is a tech demonstration. So if you're thinking about people on Mars, this experiment is designed to demonstrate that you can turn carbon dioxide in the atmosphere into oxygen. One of the reasons Mars is an exciting place for people to think about going, other than similarities with the Earth, is it has a lot of stuff that we need there. It has water vapor in the atmosphere, and they hope to find a bunch of it under the surface. Haven't found that yet, which means you can harvest water from the atmosphere. You can get oxygen from the CO2. So this is a demonstration of technologies that will be needed to support human missions to the surface of Mars. Okay, so how is this all going to work? I talked a little bit about their scientists in the loop, and you have all these tools. Well, the main goal of this mission is to identify interesting rocks and soil to bring back to the Earth. And those instruments we looked at are ways to figure out what might be a cool rock, but also the landing area has been broken up into regions of interest, places where they've looked on the delta, up the delta, where scientists have felt this is a very exciting place to look for these sorts of rocks. So these lines are showing where the rover might go. The blue spots, the blue circles are regions of interest. And the little things that show up on the second blue spot, you saw some of those in one of first Steve's plot, these little tubes. These are sample tubes. So as the rover drives around, it's a big decision. Are we going to take a sample? We only have 43 sample tubes, so you've got to be sure this is a really great rock. And then we have to leave them somewhere. where a future mission can come and get them and bring them back to the Earth. You can't just sort of toss them out the window when you're driving down the street. You have to have some thought about it. And the caching system has been developed to be very flexible. There's not a specific strategy that's been agreed upon to exactly how to take the samples and to where to leave them, but it is in process, and that is expected to happen as the mission starts. So we're going to see this in a little bit from a different perspective. This is what those blue spots would look like from above. They're not quite sure, I guess, where they're going to land yet, whether red or green, but you have regions of interest, and the rover has to drive there. And that's because it lands in a safe place. You see that big ellipse, and David talked a little bit about the landing system, and you heard some from Steve and in the video. So you land where it's safe, and you have a rover that can drive to where it's much more interesting. So you notice like the sites off to the left, they're up the delta. There's probably some vertical relief. It's not a safe place to land, but it is a place the rover can access. So as you drive along, you're using your instruments to try to figure out in these regions, what rocks have these very interesting characteristics, or the soil that is really worth using one of your 43 sample tubes that might make it back to the Earth. So here's, people have thought about this. They think about this, they simulate it. Or what if we find this many cool things and that many cool things? And this is schematically what it might look like. Oh, we think from this place on the floor, there was a volcanic flow. We're gonna get some samples there. Oh, there's olivine and carbonate. You love carbonates if you like life, because we need carbon. In other words, these are things that where people imagine they're going to find these interesting deposits. So when you start to think about how many samples you might get in a certain area, that lets you plan about how much more you might be able to explore. You don't know exactly what's going to happen until you get there, but by considering all the possibilities, you can plan a mission that's robust to all of these changes. And I put this slide in, there's a lot to read. You don't need to read it, but what I wanted you to see are these things that the goals or the objectives of characterizing these samples. These are the tests that will be done when it comes back to Earth. In other words, there's a lot of technology development going on to make things smaller and lower power so that you can go to the Earth. But it became very clear to do some of the most detailed and precise measurements that we needed to do to understand what was going on in the history of Mars and the potential for life. You really needed to have stuff in the laboratory on Earth to be able to explore these aspects. Geochronology is one of those important things. Right now, they sort of look at craters and they count how many are there of a certain size. And they've been able to calibrate that to a certain degree from the moon because we've been there, but it's nothing like bringing something back to the laboratory and making the measurements on Earth. And I think we're almost done here. So what does it look like coming, this sample return? It is actually, NASA and ESA have an agreement, and it seems to be really close. It's now at the Congress and Senate level, which might make us all feel that we're doomed. But in effect, it's a question of when it'll happen. At this point, everybody seems to think it's a good idea, but it still costs money. Right now, they're talking about things launching maybe in 2026 and getting samples back to the Earth in 2031. So there are three components. You're going to have to send another rover that zooms around and picks up all these tubes, canisters that were left there, and brings them back to a rocket, which is in the middle of the Mars ascent vehicle, because something has got to take them from the surface of Mars into Mars orbit. And then there's the Mars orbiter, which is launched separately from the Earth. And right now, I believe ESA will be the one providing that, the European Space Agency. It will rendezvous with the MAV, like not quite like in The Martian with Matt Damon, probably no Iron Man move there. But it's going to, and then so it'll rendezvous and bring the samples back to the Earth, and then they'll be let into the atmosphere of the Earth on a re-entry vehicle that doesn't have a parachute, because parachutes can fail. So they needed to design something that wouldn't crash in a way that would compromise the samples, whether you didn't want the Earth to contaminate the samples or you were thinking about the Andromeda strain. But either way, everything is being super engineered here. It's really an amazing project that is coming together. And that is the end.
Thank you so much, Mike. That was wonderful. I feel like I'm just coming away from this entire event with more of an understanding than I had about this mission initially, not just about what is it? Why are we going to send this particular mission to Mars? But what are some of the intricacies that we have to think about? And I can already tell that our audience is thinking the same way. We have lots of questions coming in. So at this point, I would love for Steve and Dave to start their webcams too. We'll do this sort of round robin style. We've got lots of questions coming in. I'll pull what I can pull, and some of them I may be able to direct to a particular person, but some of them I may not be able to, and you might just need to say, I'll take that one. So I think that we can just jump right in. Now, I did see a lot of questions about the lifespan of the particular rover. Some people are saying things like, well, previous Mars missions have far outlasted their initial planned lifespan. So how long are we expecting Perseverance to be active? What are we thinking the duration of this mission will truly be?
Mike, I'll start with
Go ahead. Go ahead.
I'll start with you, Mike. Do you know the answer? I don't know the answer to that, what their design life is.
Oh, I mean, they typically talk for the primary mission, which I believe is 1 Mars year. I don't actually know to what specifications they were designed.
So I'll speak a little on the design side. I believe you're right. I've heard 1 year for its primary mission. So on the space programs, when we design the hardware for space programs, we typically design it for worst case conditions. And what that means is we have to assess what could be the environment from a temperature side, dust, access to the sun, you name it. We have to design it for the worst case environment it could see for the life of the mission to achieve that primary science and that primary goal of, in this case, caching and taking the samples, but also reaching the duration of that goal for a year. What typically happens, though, is you don't see your worst case environment the entire time. And so you're able to actually survive longer. And you can extend your mission after you've reached that primary mission. And then you continue to extend the mission and either create new science goals or continue to evolve your science goals and to collect more data and understanding in your environment. But it's because as you design the mission side and you're doing all the engineering and requirements and figuring out what it's going to take to fly that mission and meet it to a 99 percentile or 99.9% percentile, depending on what their success ratio is or factor is, what it takes to do that mission. And then most times you don't see that catastrophic event that entire time. So we're able to get additional science and have that mission go on longer.
That makes sense. So if you plan for the worst, you're never let down. You just are always pleasantly surprised.
Your primary goal, right? And that's one of our biggest things as we go through the design. We have a requirement, and I'm forgetting the name of the word, but basically it's a requirement to say, I will be successful to this probability. And depending on the classification of the mission through NASA, NASA will set those requirements. And it may say it's going to be successful 99.99% of the time. And that's going to drive a more conservative design structure versus it only has to be successful 75%. Right? They're different ends of the spectrum as far as how you design that hardware.
That makes sense. All right, next up, I'm seeing a lot of questions come in about Ingenuity. Everything from how long is it going to fly? Is it only able to fly one time? Is it going to be able to be recharged? And then the question everybody's asking, why are we sending a helicopter flying over the surface of Mars? So what can you tell us a little bit more about some of those questions? And I think this is another one that I'll pitch to sort of whoever would like to answer it. But Dave, I think you might be a good place to start.
Yeah, I can answer the first couple parts of that. So it can fly again and again. Its limiting factor is how it basically heats up as it flies, right? The electric motors, the DC brushless motors are generating heat as part of them operating and spinning those rotors around. And that heat is ultimately the limiting factor of how much heat can it take until it has to land and cool down. It does have a solar panel on the top of the helicopter, so it can recharge in the sun and it can charge its battery. I believe its flight time is somewhere between, let's say 45 to 90 seconds, I think is what they're targeting for their initial flight or flight durations. That may, we've never flown anywhere on another planet, much less Mars, right? So that may be a conservative estimate, and they may not heat up as catastrophically as they assume. They may be able to extend that flight duration longer, or it may, due to the very light atmosphere, poor conductivity overall, it may heat up and retain heat longer, so they have to space their flights out longer. As was mentioned, I think in Mike's presentation, but it might have been in yours, Steve, the helicopter is a development effort. And what that means, it's the very first time we ever sent anything to another planet. So we're going to learn a whole lot by doing it. And so part of that, though, is there's also a lot of risk that we may fly it once, learn a whole lot, but we may learn something we didn't think about before, and it may be catastrophic. So there is a lot of risk with the helicopter. It's a demonstration to show we have that technology, that capability to be able to put something in that environment and fly it. Mars is from a flying side, is a hard environment to fly in. The atmosphere is very light. It's, what I'm blinking, I want to say it's like 1% or 10% of what the Earth's atmosphere is.
0.6%.
Right, 0.6%, there you go, of the Earth's atmosphere. And it's at about 3/8 of a G, or 3/8 of the Earth's gravity. So it's less gravity, but the atmosphere is so much weaker, it's hard to get the thrust, the lift out of that helicopter. And so it's intriguing. It's a big engineering challenge to do that. And so it's an exciting problem to tackle. So that's the engineering side. That's some of the limiting factors. And then the last part of your question was, well, why do we care about flying something at Mars? So we've landed missions where we land them and they don't move. And we do science just locally around where that lander is. In-Sight is a good example of that. The In-Sight mission we launched a couple years ago. We've landed rovers onto the surface where you can drive around and do science, and it extends our range that we can do science at and see different features. Well, we haven't landed a helicopter or some flying thing where we can now fly up and reach higher elevations or maybe more catastrophic, harder terrain to reach. When we target areas that we're going to land, we have to look at a nice flat area because we have to land in a certain ellipse. And the amount of control we have of hitting that ellipse all the way from the Earth, you know, shooting in, flying down on a parachute, or even on thrusters as we fly down, we still have to keep this landing ellipse. So it does limit where we can go and what we can go see. A helicopter or an item that allow us to fly up to more precarious or more, you know, rocky terrain or harder to reach terrain opens the door for more science.
That makes a lot of sense. And I have to just chime in and say, I feel like you said something that's really important to call out here, which is that a lot of science is just, let's see what happens. Maybe we'll learn what we think we're going to learn, and maybe we'll learn something completely different. I feel like that's a lot of what doing science and doing research is all about, is just sort of leaving yourself open to the possibility that you'll be completely surprised. This next one I'm going to send to Steve. We're getting a little bit philosophical here, but I like it. I think it's a good one. This rover, or this mission, excuse me, and I guess it is a rover, is of course hoping to help answer the question of, is there life on Mars? And we had a question from Dick wondering, so how do we define life? Why do we think that if life developed on Mars or anywhere else in our solar system or even beyond, we would actually be able to recognize it? So what can you tell us, Steve, about the search for life? What sort of signatures or signs are we looking for? And what would give us the conclusive evidence that yes, there is something here?
Well, the classic definition for life on Earth is multiple things. First, it has to be able to metabolize materials from its environment. It basically eats something in its surroundings, which provides it energy. It reproduces. It changes the equilibrium of its environment. It actually can exist by expending energy to exist. So all of those things we can, in the abstract, say, well, if we find something that meets all of these on another planet, then yes, that's life. But the only life we really know about is the life that's here on Earth. And so that guides the questions that we're asking, the instruments that we're sending, the experiments that we want to do on Mars to try and determine if Earth-like life can exist there. We have lots of research that's been done to think that maybe there are other types of chemistry that would allow life to happen rather than being based on carbon and nitrogen and oxygen like we are here on Earth. But you know, we can only ask the questions that our instruments will provide answers for, or we make the instruments to try and address the questions that we have. So it'll be a surprise if we if we are able to determine this. But I've always heard this, I'm probably mixing it up completely, but the quote that if we find life elsewhere, it's just as surprising as if we don't find life elsewhere. That either of those is a very profound statement. Either we're alone or life is easy and it should be throughout the universe. So that's,
yeah, in either case, that's pretty astounding to consider. I see another question that I'm going to direct to Mike. Several people actually popped in with something similar to this. What do you know about Mars's atmosphere? Obviously a lot, but how does that relate to effects on rovers, landers, and other things on the Martian surface? So how does the atmosphere specifically affect either working in favor of or working against the research, the data that these different crafts are trying to collect?
Well, this is really more a question for Dave. It's an engineering question, so he'll have to not make fun of me when I give the wrong answer. But basically, in terms of landing, the atmosphere helps you. It can help you slow down, but you also have to deal with it. You have to have your system be able to essentially fly or at least land safely. The moon's a different system. I mean, maybe in some ways it's harder because you can't use a parachute, but you don't have the resistance. You don't have to deal with the heat dissipation. You have those factors. But from a scientific perspective, I mean, if you have an atmosphere, so you have weather, and you've had billions of years for weather to happen. But it's even at 1% or less than 1%, it's enough to have water ice clouds. It's enough to have wind. It's enough to transport water from the poles to the center of to the equatorial region and back up to the poles. It has weather systems that look like hurricanes. I mean, we've seen some from the Hubble Space Telescope. So it has a lot of the aspects of the terrestrial weather system. So that is one thing, the dynamics. To try to understand what's happening, you need to know why does the air move around, just like weather on the Earth. So it's another system. And to do that, you need to understand what's in the Martian atmosphere. There's a lot of dust. It's a different place. There are many things the same, but there are a few differences. And the composition's a little different now. It's almost all carbon dioxide. So, but despite that, it's not a runaway greenhouse effect because the atmosphere is so thin. If you read some science fiction books, people talk about nuking the poles, you know, and getting more water vapor and CO2 to act as a greenhouse gas to warm things up. But it's probably more practical just to crash comets onto the Mars.
I think that might be the first and only time that I've ever heard crashing something into a surface of something referred to as being more practical. So we can chalk that up as a first for the evening. Dave, is there anything you want to add to that point, you know, talking about that question of how does the atmosphere or the weather on Mars affect some of the crafts that have been landed there?
Yeah, well, to your point, it's just another thing we have to design for. So I'll use a program that's currently on the surface of Mars called In-Situ. It's a lander, meaning it doesn't drive around, it sits in one place. It has solar rays for power. And one of the things that early on in that mission that we wrung our hands about is how big do our solar rays have to be and how much dust do we assume have accumulated on those solar rays and still generate enough power so we can still power the mission for the prime mission. And we wrung our hands. In the end, we ended up growing our solar ray about, I'll use inches, about 2 inches in on the radius to get extra power to accommodate the dust that can fall on it. And if you do a Google search right now, I believe NASA has images up, well, you'll see pictures of the In-Situ spacecraft that has dust on the solar rays right now. And the other counter to that we had to design to is the once in a lifetime dust devil. And that again is a terrestrial environment. You're gonna get a dust devil flying through there. It's a light environment, as I said, a light atmosphere, but it's still a real phenomenon. We see dust devils all the time at Mars, and so we have pictures from space of them. And so there's kind of two elements of that dust devil that we had to design to. We had designed to the torsional flow, but also the lift of the lift that the torsional flow makes, but also the horizontal element of that dust devil. And so those combined dictate when you're designing that hardware, how robust or strong it has to be, but also maybe how large, in the case of the solar rays, it has to be to handle that environment.
Very good. a quick answer to one that just came in related to that is, are there mechanisms to remove dust from the solar rays? Anything that a rover or a lander can do to shake it off a little bit?
Not for those. I mean, you could say design a sonic resonance system, right, that allows them to shake and try and move something, but In-Situ doesn't have that. It'd be nice if that dust devil that we had designed to could flow through it and dust him off, but it hasn't yet.
Interesting.
I should point out the dust devil scenario worked for many, many years on Spirit and Opportunity. Each of
That's
them,
very true.
you know, once a year or so, that at least they'd have the dust swept off.
Yep.
I mean,
So
hey,
is that Perseverance is powered by a plutonium power source. It doesn't use solar panels, so it's not really affected by the dust. The helicopter will be.
that's so interesting. I mean, yeah, I guess that is just something you have to plan for and try and engineer around. That's fascinating stuff. Let's see, we probably have time for a few more. Folks, I know we are past our usual 8 p.m. stop time, but we as a team felt that answering questions was something we really wanted to devote our time to. And so all of us we were willing to stay a little bit longer. So we're going a little past our usual stop time because we just want to take some questions. We just love talking to you. Let's see, Steve, I've seen a lot of questions come in about particularly the helicopter Ingenuity and what sort of instruments or what sort of experiments it's going to be doing. And I know that that's maybe more of a question for Dave. But what sort of data are you as a planetary scientist hoping that this mission will return? You know, what are you hoping to learn? And Mike, maybe you'll get some atmospheric data back or hoping to. So I guess what are we really hoping comes out of Mars 2020?
Well, certainly just a basic thing is we've only landed in 6 or 7 places on Mars in the entire history of Mars exploration. So one thing we found is every place that we go has surprises. It's a unique location. And so just seeing what it's like in this area that we know had a lake filling this crater, that's in and of itself exciting, just to see what geology is left of that. And then having this delta where water flowed into this lake and deposited sediments. So that's something that happened over some extended period of time. And to be able to look at that, you get a history of what the environment was like by going from the bottom to the farther up the stack of these layered sediments. Of course, the most exciting thing would be if they do find biosignators, and that'd be the slam dunk for all of our Mars explorations.
Yeah, that would be a pretty big day, you know, just a small discovery, just little news. No, that'd be a big deal. Great. Let's see what else we've got. We've probably only got a few more minutes before we will need to sign off, but we do still see some questions coming in. Let's see. Oh my gosh, could the dust devil totally flip the whole apparatus over? That's a quick answer from Dave, just shaking his head. I saw, or go ahead and do a quick answer to that one, and then I saw one more that I'm going to send to you.
It's even if you linearly put on the 2 biggest dust devils, one moving sideways the fastest and spinning the fastest, it's somewhere around 75 meters a second or so. And at any rate, it doesn't generate enough lift force, especially for Perseverance being as heavy as it is. It weighs like, pretty close to a Dodge Ram truck. I mean, it's stout. It's not going to flip over.
Okay, that's good to know. So The Martian, that book that has all kinds of things being flung around the atmosphere, maybe more science fiction than science fact. Dave, I see nods from all of our experts here being like, yep, it's a great book, but don't take it as fact. Steve, you and I actually saw that movie together. We went to go see a special preview of it, and the whole time you were like, that wouldn't happen. That's not real.
I realized it wasn't a documentary. I sort of liked it, but
it was really great. It's a great piece of fiction. Definitely go read the book and watch the movie, but yeah, definitely take it with a grain of salt too. One question that I did see come in that I want to have Dave answer is, how do we select landing sites? And I never realized that I had that question until, sorry if you all just heard the motorcycle go past my house. That was extremely loud. The joys of doing programming from home. How do you select landing sites? You know, what sort of criteria go into determining this is the spot on the planet that we want to put this thing down? And have there ever been sites that you've said, I really don't think that we should do that one, that you maybe would have picked something else instead?
It's really a question for Mike and the scientists, because they typically will pull together what science they want to reach, and then they'll work with the mission architects to say, here's potential regions that can do it. But I'll pass it to Mike first, and I'll maybe follow up on that.
Yeah, being an atmospheric scientist, I don't really care where they land. There's the atmosphere everywhere. But I have watched the process, and it literally can start out with 30 or 40 landing sites. Basically, it's a very community-driven process now, where anybody can submit a proposed landing site, and they have meetings, and you can go and you can make your case. And in that sense, it's probably a little too political. They start canvassing and things, but it's supposed to be decided by the science in that sense. But as Dave mentioned, there are fundamental engineering constraints. They tend to be near the equator because it's easier from the celestial mechanics, the orbits, to get to those locations. It wants to be below a certain altitude because the parachute needs to have a certain amount of ability to slow things down. A lot of people would love to go to the top of Olympus Mons or one of the other tall volcanoes, but it's just not practical with current landing systems. So it's a very science-driven. It depends on the mission emphasis, you know, so you have to take the mission goals where people think you can accomplish these goals, and then you fold in the engineering.
Makes a lot of sense. All right, with that, I'm going to wrap us up with just a couple of last details. Number one is that if you have not tuned in for a virtual program before, you might not be aware of this, but if you have, especially if you've caught Digital Earth before, you might be aware that we have a couple fans who occasionally will feel inspired to write us haikus in the chat. And when that happens, I often like to share them out. So tonight we have one coming from Judy. Her haiku, excuse me, is the following: Perseverance soars, Marsward to explore, filled with ingenuity. I think that's pretty awesome. That's the mark of a good program when you get a haiku out of it. So thank you, Judy, for that one. And last but not least, Steve and I did want to just plug a couple of additional resources that you're welcome to take a look at. So I'm going to share my screen again. If there is anything that you would like to learn more about, these are some great resources for you. So NASA's Mars missions, NASA TV, and launch updates. So mars.jpl.nasa.gov, and then nasa.gov/multimedia/NASA TV, and then launch updates at spaceflightnow.com. And then as a final plug, on Thursday, this is when the March 2020 mission is launching. It is headed for the Red Planet, launching at 5:50 in the morning Mountain Time. And it's going from Florida, is that correct? And I know we have a few people watching from other time zones today, so you may have to do the conversion. But regardless of what time it's happening where you are at, Steve and I are actually going to be live on the museum's Facebook page. So facebook.com/dmns.org, I believe, and you'll be able to check us out. You'll get to hear a little bit from Steve about the mission, catch some more details, and then we will switch over to streaming the launch live from NASA TV. So we will be in the building at the absolute crack of dawn, before the dawn, ready to talk space and share our excitement about this mission with you. So make sure you tune in on Facebook to watch us. We'll go live at about 5 o'clock in the morning that day with the launch at 10 till 6. So make sure you tune in, get up nice and early, have your coffee, and talk some science with us. Thanks for tuning in, everyone. It was wonderful to have you, and a huge thanks to all of our panelists who were part of this today. Thank you, Mike. Thank you, Steve. Thank you, Dave. And thank you, Tatiana from Lockheed Martin, who is behind the scenes a little bit. She's running things on the back end today, but we couldn't have done it without her. So thanks to everybody. Thank you for tuning in. We can see that your nice comments are coming into the chat, and that always makes our day. So thanks, everybody. We're going to go ahead and sign off. Stay curious, and we'll see you next time. Bye, everyone.
Thank you.
Bye.